Hi everybody, this is notes for 7.2 sample proportions. So if I'm interested in finding the true proportion of blue M&Ms, if I can't possibly count them all, how should I go about doing that? Well, we find the mean of the sampling distribution, right? So we're going to take samples and using a certain number of SRS samples. That makes sense. So what do I know that will lead to a more accurate estimate of the true proportion of blue M&Ms? So if we're going to do the sampling, what things should I pay attention to? So the first one is I should be using a large sample size. Use large sample size. Okay, remember we use little n for that, so we could use like large, like 100, right? In our class yesterday, we played with 2s, 5s, and 25s, and we saw that at 25, we started to see some interesting things happening. So if we have the ability to pick, let's pick something really big, like 100. Okay, the other thing we want to do is we want to take many, many samples. Right? We're not going to be able to do an entire sampling distribution for this. So the best thing we could do is just take many, many, many samples. And then the last thing we want to do is we want to make sure those samples are randomly selected. So make sure samples are randomly selected. Okay, cool. So in this example, let's see if we can identify the population, sample, parameter, and statistic. So remember that the population are the who's or the what's, and the parameter and the statistics are the numbers. So the population would be all of the, let's see, what am I taking a sample of? I'm going to start there. So the sample would be sample of 100 M&M candies, right, would be my sample, and I'd be counting up the proportion of blues in that. So that's going to be our statistic, is the proportion of blue M&Ms in 100 candies. Okay, and then let's see, the population then would be all M&M candies. So we're picking 100 out of, right, wherever, all M&M candies. And our parameter would be the true proportion of blue M&Ms in the population. Okay, what symbols do we use? So for parameter, we're going to be using just the regular p or pi. And then for our other one, this one is going to be the p hat. Okay, so I usually start with what am I sampling, what am I taking? So how do I calculate a p hat, right? So we're just going to take the number of M&Ms over the sample size. So we're going to call that big X, the number of M&Ms, just like we would have done for random variable, over the sample size called little n. Okay. All right, and then a quick review. Which ones are unbiased estimators of a population parameter? In other words, what sampling things are going to be close to the real population? Would the mean be the same of anything? If I were to do a sampling and assume we're doing it well, would it be an unbiased estimator? Yes, this one would be. Standard deviation. Well, we learned that the bigger the sample size, the smaller the standard deviation, so this one would not be. What about range? So if I looked at the range of the whole entire population, let's say if I was doing a means problem, would that be the same for the sampling distribution as it is for the whole population? I'm going to say maybe. And then what about median? If I do the median, that should work out just like mean, right? So range is the only one of like, would that be any different? Like, let's go back to what we were doing yesterday in class and think about like when we were doing those things, was there anything major happening there when we were calculating the means of those chapter 6 scores? So if I took the range of the actual population, those would be the individual scores. And then if I took a range of a sample, yeah, I should still get the same, right? I think so. Okay. All right, so how do we calculate p hat? standard deviation of the sample, standard deviation of the whole entire thing. So the mean proportion of the sampling distribution should be exactly the same as the true proportion of the population. If we sample well, our mean proportion from our sampling should be the same as the true proportion. Another way to say that is if we do this well, p hat should equal p. And the standard deviation of the sampling distribution gets bigger or smaller than the standard deviation of the true proportion. The standard deviation of the true proportion is already set. We just don't happen to know what it is. The standard deviation of a sampling distribution gets smaller as we get smaller than the standard deviation of a true population. And as sample sizes increase, standard deviation decreases. Okay, all right, so just as a review, don't really need to worry about these until we get to the formula on the next page, but remember from chapter 6 when we were doing random variables, we had this was the way to get to an average of your random variables, this was the way to get to your standard deviation of random variables, and for M&Ms we can use a random variable binomials because either the M&Ms are blue or they're not, so this works as a binomial, okay? And again, we talked about how p hat was just the number of what we want out of the sample size, x over n. So our new means and standard deviations are gonna be on the next page. And they are right here. This is really exciting, I know, okay? So the average of p hat should equal p. Well, we just said that in the previous thing. Okay, so if you know to find the average of a whole bunch of proportions, that should equal the true proportion. The standard deviation of a true proportion is going to be this, and this is in your formula sheet. It's right there. It'll put it under binomial for you so that you know to use it. Okay, so the only thing that makes it different from the one we had before is the one we had before didn't have the denominator, right? So now we're going into proportions, so we have the 1 over the n, just multiplying by a constant. So we've got the n in the denominator now. Cool. All right, so the big thing you need to know is to find the mean, it should just be p, and to find the standard deviation, we have this formula, okay? So we know from yesterday from our last class that sampling distributions do tend to look approximately normal if the sample size is large enough, right? So we can use our normal curves then on these types of problems to calculate probability under the curve using z-scores, using norm CDF with our calculator. And we like to do that because that's something we're comfortable doing and we're going to continue doing it for the entire year. So being able to get to a z-score in normal CDF is well worth the work. So here's the problem. In order to go to a normal, there's 2 rules we have to check first. Rule number 1 is the 10% rule. This one allows you to use your standard deviation formula that I just highlighted. If it doesn't pass the 10% rule, we are done because it'd be a different formula that isn't part of this course. Okay, so they're having you check it, it should work, but they're still going to ask you to check it. So here's how you check the 10% rule to make sure we can use our standard deviation formula. It's that 10 little n is less than or equal to big N that we introduced last semester. Okay, so I need this in order for this binomial probability problem of proportions to go into a normal calculation. All right, so how do I do that? Okay, little n, remember, is your sample size. Big N is your population size. Okay, I need to make sure that however many M&Ms that I sampled, those M&Ms where I'm counting the blue ones, I need to make sure that my scoop size is not more than 10% of all M&Ms in the universe. Okay, so that's the 10% rule. It's also kind of called independence too. You'll hear it talked about as an independence check later. Same idea. We want to make sure that we're not significantly changing any proportions. And as long as what we're scooping is less than 10% of the whole population, we should be good there. Okay, so in our case, if our scoop size was 100, let's go check that. If I put in 10 times 100, is that less than or equal to, I don't know how many M&Ms there are in the universe. So in this form of the equation, the numbers are all together. That's great. Okay, so I have 1,000 is less than or equal to the the population size. Can we agree that there are more than 1,000 M&Ms in the universe? Yes, so it passes this check, so I'm allowed to use the standard deviation formula. Okay, so often you won't know what big N is, but you do know what little n is, and you're just basically going to say that my calculation does appear to be less than the entire population. So we think there is more than 1,000 M&Ms. Okay, so check mark, we're good. All right, the second rule we have to double check is called a large count rule. This one lets us go to normal. This one is the one that lets me do norm CDF. So this is the one I have to check in order to do norm CDF. Okay, so in this one, it's going to be this formula right here. Little n times little p has to be bigger than or equal to 10, and little n times 1 minus p has to be greater than or equal to 10. So basically we're saying there must be at least 10 of what I want and at least 10 of what I don't want. So if my sample size was 100 and my proportion of blue M&Ms, I don't know, we never talked about it, so let's make one up. Let's say in my sample it ended up being, let's do 50%. Okay. All right, so if it's 50%, then I could look at that and say, is that going to be more than 10? Well, this is going to be 50, right? That's more than 10, we're good. And then I also have to check the other half. So 1 minus 50% is still another 50. So we're also good on how many are blue and how many are not blue. Now that 50% I just made up, right? They would have to give us information about what the proportion is of blues, either in the entire population, which why would we know that, or in our sample. Okay, so let's apply these. We just did basically, but now they're going to give us the numbers to actually use for this. So let's apply to the M&M. Suppose it's been stated that 20% of the M&Ms are blue. Okay, that's the population that we think we're working with. What is the probability that the proportion of blue M&Ms is less than 15%? Okay, of if the sample size is 60. All right, so this is my sample. They're like, how likely is it for me to get 15% blue or less? Okay, so I gotta check the 10% rule. The 10% rule is 10 times n. So 10 times 60, is that less than the universe of M&Ms? I believe so. 600 is less than all M&Ms. We should be okay. For the large count rule, that one is going to be the n times p, so n is 60 and p is the 20%. So we multiply by 20%. That should be greater than or equal to 10. So 20% is 12, so we're okay on this side. And then we also have to check that 60 times 1 minus 20% is also more than 10. So 60 times 80 should be more than 10. And again, if we already used up 12, that still leaves us 48 out of the 60, and that works as well. So now we're allowed to use normal CDF, okay? All right, so now I can go ahead and draw my curve. And, right, what we have is they're saying that they think the true proportion is 20. They're telling us we're at 15. They want to know what the likelihood is that we're less than 15 when we do a sampling. Okay, so we are looking at that this has a standard deviation of, here is our standard deviation formula. So our standard deviation formula was p times 1 minus p over n. Okay, so I'm going to go and put that into my calculator exactly how it's written here, norm CDF, and I'm going to actually put in the entire formula because I never calculated it before. So you can calculate it ahead of time, just write out enough decimals that you feel comfortable. So I'm doing negative 10 to the 10th for norm CDF. My upper is, oh, yes, my upper is 15%. My average proportion was 20%. And my standard deviation is going to be a humongous square root of 0.2 times 0.8 all divided by 60. Okay, and again, to get this on my calculator, I'm pressing blue VARS and then norm CDF. So I am getting that this equals 0.1664. So the probability that my sampling would be less than 15% blue if the true population was actually 20% is about 16.6%. Okay, that's it.